we now want to go about actually solving this problem for these currents in this circuit. So let's suppose we have a 12-volt battery, a 12-ohm resistor, a 6-ohm resistor, and an 8-ohm resistor in this configuration. Now, as we said before, we can actually find the currents using series and parallel circuit rules, and we'll do that at the end and show that this is consistent with those, but let's just see how Kirchhoff can be applied to get us started with these types of problems. So let's first apply the junction rule, and we'll do it the same way as we did in the last video. I1 is leaving the battery, hits this junction, and I2 moves through this branch, and I3 moves through that branch. So we can say that I1 is equal to I2 plus I3. Now, we want to use the loop right here, and again, you can use any loops that you want, okay? You are not restricted to the loops that you want. You have 3 at your disposal, you just need to use 2 of them. I'm going to use this one, and I'm going to use this one, the 2 that I talked about in the previous video. So if we start here at the battery, and we go clockwise around the loop, we see that we traverse the battery from the negative terminal to the positive terminal. So in my second equation, this is going to be 12 volts. And then I traverse I2, or actually resistor 2, this 12-ohm resistor, in the direction of I2, so this is a drop in voltage. And I'm going to drop the units on the ohms, assuming that we recognize that all of the numbers that don't have a voltage attached to them are ohms, and ohms times amps is volts. So negative 12 times I2, and then we come across this 8-ohm resistor, so this is going to be minus 8I1, and all of that must add up to 0. Now if we go across the top, right, what we're going to see is that we traverse the 6-ohm resistor in the direction of I3, so that is a drop in voltage, and we go across the 12-ohm resistor against the direction of the current, so this is a increase. Okay, so now here are my 3 equations. And how do I solve a system of 3 equations? Well, one thing that you'll notice is that in my bottom 2 equations, right, I have I2 in both of those. So I2 may be a good place to start. There are several different methods for solving systems of equations, but without computers or appealing to matrices, linear algebra, one of the better methods is substitution and elimination of a variable. So since I have I2 in both of these equations, it might make sense to solve equation 1 for I2 and then insert that into these 2 equations and see what happens. So if I look at equation 1 and solve it for I2, I get that I2 is equal to I1 minus I3. All right? So I'm now going to insert that into the second equation. Right? And if I simplify this, and of course this is equal to 0, if I simplify this, I'm going to get 12 volts minus 12I1 plus 12I3 minus 8I1. And simplifying further, I'm going to get 12 minus 20I1 plus 12I3 is equal to 0. Okay, so this is our new equation 2. And to save space, I'm going to rewrite this equation up here where equation 2 is. And in fact, I'll go ahead and rewrite equation 1 as well. Okay, so equation 2 now says minus 20I1 plus 12I3. Okay? And now I'm going to do the same process in equation number 3. I'm going to insert I1 minus I3 in for I2 here. And doing that, is going to give me this, negative 6I3 plus 12 times I1 minus I3 equals 0. Close those parentheses. And going to get negative 6I3 plus 12I1 minus 12I3 equals 0. Okay? And again, I can add these up. And now I'm going to get 12I1 minus 18I3 is equal to 0. So now I can replace this equation okay. And before we go any further, let's review what I've done. I've simply taken I2 and eliminated it from the bottom two equations. Now I have two equations with only two unknowns. So I've reduced my system from 3 unknowns down to 2 unknowns, and I only need 2 equations for that. So it doesn't matter at this point which variable we want to solve for. Why don't we go ahead and solve for I3 in this equation here? So if I take 18I3, I'm adding 18I3 to this side, so it's going to be positive, and that's going to equal 12I1. Then I3 is going to equal 12/18 of I1, and 12/18 is the same thing as 2/3. Okay. So now I can insert this. This was equation 3, and I'm going to insert into 2. Okay, I'm going to insert this into equation 2. So I'm going to insert this result, 2/3 I1, into here, and then I will have just one equation with one variable. All right. So then I'm going to get 12 volts minus 20 I1 plus 12 times 2/3 I1, and all of that equals 0. Okay? So this is going to be 12 volts minus 20 I1 plus 12 times 2/3 is 8, right? So I'm going to get 8 I1, and all of this must be 0, and 12 volts, negative 20 I1 and 8 I1 is negative 12 I1. And from here, if I add 12 I1 to both sides, I get 12 I1 equals 12 volts, and therefore I1 is equal to 1.0 amps. So what that means is I have 1 amp running through this branch right here. Okay, I have 1 amp running through that branch right there. So now I can use this result to get I3 very easily, and then once I have I3, I can get I2. So remember that there was the relationship I3 was equal to 2/3 I1, and we take 2/3 of 1 amp, and that is 0.667 amps. And now that we're here, all we need to do is use this first relation to solve for I2. So I2 is going to be equal to 1 amp minus 0.667 amps, which is 0.33 amps. Okay, and as I said before, we could have deduced this just using the rules of parallel and series circuits, right? And let me outline how we'll do that. Okay, let me outline how that would be done, just ever so briefly. So, recap, what's happening here is we have 1 amp flowing through this large branch where the battery is, and then 1/3 of it goes through I2, and 2/3 of it goes through I3. So, for every 3 electrons that flow through I1, when those 3 electrons hit this branch, 1 of them will go through I2 and 2 of them will go through I3. All right. So if we wanted to use series and parallel rules, what we could do is combine these two in parallel, and what you would find is that if I combine 2 resistors of 6 and 12 ohms in parallel, then the R equivalent for that would be 6 times 12 divided by 6 plus 12, and that turns out to be 4. Okay, so this combination has a equivalent resistance of 4 ohms, and that combination is in series with this 8 ohm resistor, and so the total resistance in the circuit would be 4 plus 8 ohms, which is 12 ohms. So the total resistance in the circuit is 12 ohms. My battery can supply 12 volts. So my current that the battery is producing is indeed 1 amp, just as we found using Kirchhoff. Now, in most cases, everybody would say that, you know, for this particular circuit, I would highly recommend you use the series and parallel rules. Much quicker. We just outlined it in a few steps here, as opposing to doing a board work or several boards worth of work. All right, but it does show you that Kirchhoff's rules can be applied to these circuits. Right. So in the next video, we will work through an even more complex circuit where we have to use Kirchhoff's rules, and we cannot use anything else.